Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics with a focus on networking. Today, we're diving deep into DNSSEC, the Domain Name System Security Extensions. This is one of the most important yet misunderstood security technologies on the internet. Let me start with a story that illustrates why DNSSEC matters. Imagine you're in a foreign city asking for directions. A stranger confidently points you down a dark alley. Would you trust them? That's essentially what happens billions of times daily with DNS. Your computer asks where is google.com and trusts whatever answer it gets. No verification, no ID check, nothing. DNS is the internet's phone book, translating Amazon.com into IP addresses like 205.251.242.103. It's brilliant in its simplicity, but that simplicity is also its greatest weakness. DNS was designed in 1983, when the internet was a trusting community of researchers. Security wasn't a concern. The entire system was built on trust. Today, that trust model is catastrophically inadequate. Cybercriminals actively exploit the DNS lack of security through cache poisoning attacks. The consequences are devastating. Imagine logging into what you think is your bank, but you're actually on a criminal's server. This happens every single day. DNSSEC was developed to solve this fundamental flaw by adding cryptographic signatures to DNS responses. But DNSSEC had to work with existing infrastructure. We couldn't throw away DNS and start over. It had to be backwards compatible, incrementally deployable, and maintain the speed that makes DNS work at internet scale. That's an incredible engineering challenge that DNSSEC elegantly solves. The DNS security problem. Let me paint you a picture of exactly how DNS attacks work. This isn't theoretical. These attacks happen constantly, and they are devastatingly effective. When you type bank.com, your computer asks your ISP's DNS resolver. The resolver queries root servers for .com handlers, then asks the .com servers for bank.com handlers, and finally gets the IP address. At any point, an attacker can inject false responses. Cache poisoning is particularly insidious. An attacker races the real DNS server, sending fake answers that arrive first. Your resolver accepts and caches this poisoned response. Now everyone using that resolver gets directed to the attacker's server. The Kaminsky attack in 2008 showed how trivially easy this was at a massive scale. Man-in-the-middle attacks are another vector. On public Wi-Fi or through compromised routers, attackers intercept your DNS queries in real time. They see newssite.com and redirect you to propaganda sites instead. DNS hijacking compromises the servers themselves. The 2019 Sea Turtle campaign targeted national security organizations this way. The financial impact is staggering. Single attacks can redirect millions in cryptocurrency, steal thousands of banking credentials, or take down major services. The 2016 Mirai botnet DNS attack against Dyn took down Twitter, Netflix, Reddit, and dozens more. What makes these attacks so effective is their invisibility. When redirected to a fake site, your browser shows the correct URL with a valid SSL certificate, which is increasingly easy to obtain. You see the reassuring padlock. Everything looks legitimate, but let's dive into how DNSSEC actually works. At its core, DNSSEC uses public key cryptography, the same technology securing your online banking. Every DNS zone has a pair of cryptographic keys. A private key kept secret and a public key published for everyone. Think of it like a medieval king's wax seal. The king has a special seal only he possesses, which is the private key, and everyone knows what his authentic seal looks like, which is the public key. When sending messages, he seals them with his unique seal. Anyone can verify authenticity by checking the seal. DNSSEC works similarly. When a DNS server has a record like www.example.com is 93.184.216.34, it creates a digital signature using its private key. This signature proves two things. The record came from the authentic DNS server and hasn't been modified. The signature is a complex mathematical operation. The server takes the record data, combines it with validity periods, runs it through a cryptographic hash function producing a unique number, then encrypts this number with its private key. The result is the digital signature. When your computer receives a DNSSEC response, it gets both the answer and the signature. To verify, it uses the public key to decrypt the signature, revealing the original hash. It then hashes the DNS record itself. If the hashes match, the record is authentic and unmodified. But how do you know the public key is authentic? This is DNSSEC's genius, the chain of trust starting at the DNS root. Each level vouches for the level below, creating an unbroken chain of cryptographic trust. Crucially, DNSSEC doesn't encrypt DNS data, it only signs it. Your queries remain plaintext. DNSSEC ensures authenticity and integrity, not confidentiality. It guarantees you're talking to the real DNS server with unmodified answers. The beauty is transparency. Resolvers handle all cryptographic verification behind the scenes. The chain of trust. The chain of trust is DNSSEC's most elegant aspect. At the very top sits the root zone, represented by a dot. The root zone's cryptographic keys are so important they are managed through elaborate ceremonies that seem straight from a spy thriller. 4 times yearly, in secure facilities in California and Virginia, trusted individuals from around the world gather for the root KSK ceremony. These ceremonies require multiple people with different access credentials, meaning no single person can access the keys alone. Everything is filmed, broadcast live, and meticulously documented. The hardware security modules are kept in safes that require multiple people to open. So, why such extreme measures? The root key is the ultimate trust anchor. If it were compromised, the entire DNSSEC system would be vulnerable. This key signs all top-level domain keys, such as .com, .org, .net, and every participating country code domain. Here's how the chain works. The root zone signs .com's DNSSEC keys, essentially saying, I vouch these are legitimate keys for .com. The .com zone signs example.com's keys, and example.com signs its own DNS records. This creates an unbroken chain of cryptographic trust from the root all the way to specific records. The technical mechanism is the DS, or delegation signer, record. When you enable DNSSEC, you provide your DS record to your parent zone. This DS record contains a hash of your DNS key record, creating the cryptographic link. Validation follows this chain in reverse. Your resolver starts with the trusted root key, uses it to validate .com's key, then validates example.com's key, and finally validates the actual DNS record. If any link in the chain breaks, validation fails. This mirrors the DNS hierarchical structure, enabling incremental deployment. Not every domain needs to be signed for DNSSEC to provide value. As more domains adopt DNSSEC, these islands of trust connect into continents of secured DNS. Let's explore the 4 new record types introduced by DNSSEC. Each one plays a crucial role in the security system, and understanding them will help you troubleshoot issues and appreciate its elegant design. RRSIG, which stands for Resource Record Signature, is the workhorse. Every DNS record that needs protection gets its own RRSIG record. For example, when you query an A record, you get back both the A record and its corresponding RRSIG record. The RRSIG contains the digital signature plus metadata, such as the creation time, expiration date, the algorithm used, and which key was used to sign it. RRSIGs expire, typically within a week to a month. This means they require regular re-signing. Why not sign once? If a key is compromised, you want signatures to expire. It balances security and operational overhead. I've seen many failures from expired signatures when automation fails. DNS key records contain the public keys used for verifying RRSIG signatures. Zones typically have 2 types of keys, a zone signing key, or ZSK, which signs regular records, and a key signing key, or KSK, which signs the DNS key records. This separation is crucial for key management. Next are DS, or delegation signer, records. These create the chain of trust between parent and child zones. It is a hash of a child's DNS key that is stored in the parent zone, acting like a parent's endorsement. When you enable DNSSEC, you provide these DS records to your registrar, who then passes them on to the registry. NSEC/NSEC3 records handle authenticated denial, which is a way of proving that a domain name does not exist. NSEC creates a sorted chain of all the names within a zone. Each record points to the next name in the chain and lists the record types that exist for the current name. By walking this chain, you can prove that a specific name does not exist between two valid names. NSEC3 improves on this by using hashed names. This prevents zone enumeration, which is the act of listing all names in a zone, while still providing proof of non-existence. These four types work in concert. DNS key provides the keys, RRSIG provides the signatures, DS creates the chains of trust, and NSEC and NSEC3 prove non-existence. If you remove any one of these components, the entire security model breaks down. Understanding these records is crucial for successfully implementing and troubleshooting DNSSEC. Let me walk you through what happens when you query a DNSSEC-enabled domain. This validation process is a carefully choreographed dance, happening in milliseconds across multiple servers. When you query www.example.com, your computer contacts its DNS resolver, which is typically your ISP's or a public resolver like 8.8.8.8. If the resolver supports DNSSEC validation, and this is increasingly the default, it doesn't just fetch the answer. It validates the entire chain of trust. The resolver starts with a trust anchor, the root zone's public key, which is hard-coded into its configuration. This is the foundation of all validation, the one piece of information the resolver inherently trusts. The resolver might have cached information from previous queries. If it has a validated .com DNS key cached, it can skip to validating example.com. But let's assume it's starting fresh. First, it queries root servers for the .com nameservers, receiving DS records and RRSIG signatures. Using the root's public key, it validates these signatures. If they are valid and not expired, it trusts the DS record, which contains a hash of the .com DNS key. Next, it queries the .com servers for the nameservers of example.com, and for the .com DNS key records. It verifies that one of the keys matches the DS record hash, proving these are legitimate .com keys. Now it can validate the DS record for example.com. The process continues down the chain until it validates the actual record for www.example.com. The resolver checks signatures, expiration times, inception times, algorithm support, and key tag matches. Any failure results in a serve fail response. It's better to get no answer than a forged one. DNSSEC validation is all or nothing. Either the entire chain validates perfectly, or the query fails. This strict approach prevents downgrade attacks. The performance impact is minimal thanks to caching, as the keys for popular domains stay cached for nearly instantaneous validation. Key management in DNSSEC is where its operations get really challenging. The fundamental problem is that cryptographic keys shouldn't be used forever, but DNS records are cached everywhere. If you change keys carelessly, your domain can disappear from the internet. DNSSEC uses two-tier keys for easier management. The key signing key, or KSK, is your master key. It's larger, at 2048 plus bits, changes rarely, perhaps every 1 to 2 years, and it only signs other keys. The zone signing key, or ZSK, is your daily key. It is smaller, between 1024 to 1536 bits, changes frequently, about every 1 to 3 months, and it signs all DNS records. So why are they separate? The KSK is critical. If you lose it or compromise it, you are in serious trouble. You should keep it extra secure, perhaps offline in hardware security modules. You only use it to sign new ZSKs. The ZSK does the heavy lifting of signing records, so it must be online and automated. Changing your KSK requires updating DS records at your parent zone through your registrar, which is often a manual process. But changing ZSKs is an internal process. As long as the new ZSK is signed by the same KSK, validators will accept it. Key rollover requires careful timing. To do this, you use a double signing rollover. First, you introduce the new key alongside the old one and sign with both. Then, you wait for caches to update, which is at least 1 TTL. After that, you stop signing with the old key but continue to publish it. You wait another TTL, and then you can finally remove the old key. This process takes days or even weeks. Rushing it will cause validation failures. The 2018 root zone KSK rollover took years of planning. ICANN ensured every validating resolver knew the new key, delaying the rollover multiple times when data showed that resolvers were not ready. It really showed how challenging key management is, even with extensive planning. Automation is essential. Tools like DNSSEC can handle this complex timing automatically. However, it's important to understand the process for when that automation fails. Emergency procedures for compromised keys are also critical. Be sure to document everything, test regularly, and always respect the complexity of key management. Let's discuss the benefits of DNSSEC and its real-world impact. The benefits extend far beyond preventing DNS spoofing into areas you might not expect. First, DNSSEC provides authentication and integrity. When you visit your bank's website, you are confident you are actually reaching your bank. When systems connect to cloud services, they connect to the real services, not imposters. I have investigated incidents where companies lost millions of dollars to DNS hijacking of cryptocurrency transactions. With DNSSEC, these attacks are cryptographically impossible. DNSSEC also enables other security technologies. For example, DANE, which stands for DNS-based authentication of named entities, publishes TLS certificate information in DNS, all secured by DNSSEC. This solves the certificate authority system's vulnerability to compromise. With DANE, you can specify exactly which certificate or CA should be used, which prevents fraudulent certificates. I have seen DANE prevent attacks where nation-state actors obtained fraudulent certificates from compromised CAs. Email providers like ProtonMail use DANE to ensure that encryption keys cannot be silently replaced. It is becoming critical for secure communications. DNSSEC also enables SSHFP records, which are SSH fingerprints in DNS instead of getting the message. The authenticity of host cannot be established. SSH verifies the server's fingerprint against DNSSEC signed DNS records. This prevents man-in-the-middle attacks on SSH connections. Authenticated denial of existence prevents attackers from claiming your subdomains do not exist or from redirecting non-existent subdomains to malicious sites. For email security, DNSSEC protects DMARC, SPF, and DKIM records from being modified. Major providers prefer DNSSEC signed domains because they are harder to impersonate. DNSSEC provides legally admissible evidence of DNS tampering. It transforms DNS from a he said, she said situation into cryptographic proof. As more domains adopt DNSSEC, the entire internet becomes more trustworthy. In fact, even unsigned domains benefit from fewer opportunities for cache poisoning. Challenges and considerations. Let's have an honest conversation about the challenges of DNSSEC. I've implemented it for organizations from small businesses to Fortune 500 companies, and I've seen every way it can go wrong. The biggest challenge is complexity. DNS is already complex, and DNSSEC adds cryptographic operations on top. One major e-commerce site enabled DNSSEC before Black Friday. Everything tested fine, but they didn't account for the configuration of their CDN when deployed. 30% of users couldn't reach the site. They lost millions before rolling back. DNSSEC is fragile. Regular DNS degrades gradually with misconfigurations. With DNSSEC, one wrong move and your domain disappears. Forget to update DS records after key rollover? Domain gone. Let signatures expire? Domain gone. Misconfigure signing? Domain gone. Response size is a major challenge. DNSSEC increases DNS responses by 3 to 8 times. A 100-byte response becomes 800 bytes with signatures. This requires eDNS0 or TCP fallback. Some firewalls drop large DNS packets or block TCP port 53, configured years ago when large responses were suspicious. DNSSEC doesn't provide confidentiality, as queries remain plaintext. Many assume DNSSEC encrypts traffic, but it only ensures authenticity. You need DNS over HTTPS for privacy. The amplification attack risk is serious, as large responses can be abused in DDoS attacks. Debugging failures is difficult. Resolvers return generic serve fail errors with no indication of DNSSEC problems. I've spent hours tracking failures from clock skew, algorithm mismatches, or subtle errors. You need specialized tools and expertise. The adoption chicken and egg problem slowed deployment. Operational overhead is significant, including monitoring expiration, managing rollovers, and maintaining infrastructure. Cost includes hardware security modules, monitoring, training, and cloud service premiums. Despite these challenges, DNSSEC is worth implementing. Start with non-critical domains, test thoroughly, have a rollback plan, monitor religiously, and train your team. The challenges are manageable with proper preparation. Real-world DNSSEC deployment. Let me share the real state of DNSSEC deployment. Where we are, how we got here, and what the future holds. It's a story of slow but steady progress, with surprising successes and frustrating setbacks. As of 2024, adoption varies wildly. The .gov domain mandated DNSSEC in 2008, and today nearly 100% of federal domains are signed. This proved DNSSEC is deployable at scale with sufficient motivation. The .bank and .insurance TLDs require DNSSEC for all domains. You cannot register without it. Country code TLDs tell interesting stories. For example, the Netherlands, .nl, has over 90% adoption, which is the highest globally. Their registry made DNSSEC free and easy, providing tools and support. Sweden, .se, and the Czech Republic, .cz, have similar success through proactive programs. But for .com, which represents a vast number of domains, there is under 5% adoption, due to legacy systems and varied registrar support. The resolver side is encouraging. Google Public DNS validates DNSSEC, handling a massive volume of queries daily. Cloudflare's 1.1.1.1 validates by default. Major ISPs like Comcast enabled validation. Even if your domain isn't signed, you benefit from validation of domains that are. Enterprise adoption accelerates after high-profile attacks. The 2019 Sea Turtle campaign made organizations realize their vulnerability. E-commerce sites worry about performance during peak seasons. Media companies struggle with CDN complexity. Small businesses lack expertise and rely on hosting providers. Registrar support remains inconsistent. Some make DNSSEC one-click easy. Others require manual DS updates via tickets. Budget registrars often don't support it at all. Cloud providers now support DNSSEC, though often as premium features. Recent attacks accelerated adoption. The 2020 Twitter DNS attack and 2021 Exchange server vulnerabilities drove implementations. Looking ahead, mandatory adoption works while voluntary remains slow. We're approaching a tipping point where DNSSEC becomes default rather than the exception. The tools exist, and the benefits are clear. What's needed now is the will to deploy it universally. My prediction? Within 5 years, DNSSEC will be as standard as HTTPS is today. The question is how many attacks we'll endure before we get there. DNSSEC tools and commands. Let me show you essential tools for working with DNSSEC. These are not just commands. They are your weapons in the fight for DNS security. I will share the exact commands I use daily and tricks that have saved me during troubleshooting sessions. The dig command is your Swiss Army knife. Adding plus DNSSEC requests DNSSEC records. But dig does not validate by default, it just shows you the records, which is useful for debugging. When I run dig plus DNSSECexample.com, I look for RRSIG records to see if the zone is signed, and for the AD flag. An AD flag of 1 means it was validated, while an AD of 0 means it failed or there was no validation. Pro tip. Using dig plus trace plus DNSSECexample.com shows the entire resolution path. This is invaluable for debugging chain of trust issues. The plus CD flag, which stands for checking disabled, returns results even if validation fails. You can compare regular queries with plus CD to identify DNSSEC problems. For specific records, the command dig DNSKeyExample.com shows public keys, where you should look for flags 256 or 257. The command dig DSExample.com at parent nameserver checks if DS records are published. DNSViz creates visual graphs of validation chains, which is excellent for explaining issues. VeriSign's debugger provides plain English explanations. For key management, the command DNSSEC keygen with the parameters AECDSAP256SHA256, B256, and endzoneexample.com will generate your keys. Use inline signing instead of the manual DNSSEC sign zone command, as manual signing is error-prone. You can monitor your configuration by using DNSSEC verify with the O parameter for example.com and your zone file in your scripts. Here is a troubleshooting technique. Query multiple resolvers like 8.8.8.8, 1.1.1.1, and 9.9.9.9. Any disagreement between them likely indicates timing issues. Use the delve command for DNSSEC-aware queries that include validation. For Windows users, you can use the resolve DNSName command in PowerShell with the name parameter set to example.com and the DNSSEC OK switch. Here is an emergency checklist. Check if the zone is signed. Verify the signature expiration. Confirm the DS and DNS key records match. Test with the plus CD flag, and use DNSViz. Remember, failures are almost always due to expired signatures, DS mismatches, unsupported algorithms, or time sync issues. As we wrap up this deep dive into DNSSEC, let me leave you with some hard-won wisdom from years of implementing and operating DNSSEC in production. These are not theoretical best practices. They are lessons learned from outages, near misses, and successful deployments. First, respect DNSSEC's complexity. I have seen overconfident engineers enable DNSSEC on production domains without proper testing, which took their companies offline. DNSSEC is unforgiving. There is no such thing as mostly working. Either everything validates perfectly, or your domain disappears from the internet. You must approach it with extreme caution. Start with non-critical domains. Register test domains specifically for learning DNSSEC. Break them, fix them, and practice key rollovers until it becomes boring. Only after you are completely comfortable should you even consider touching production domains. I personally keep several test domains just for experimenting. Automation is absolutely essential. Manual DNSSEC operations are a guarantee for disaster. You should use tools like OpenDNSSEC, PowerDNS with automatic signing, or cloud services that handle DNSSEC for you automatically. The cost of automation is tiny compared to the cost of an outage. We have seen million-dollar sites go down simply from a forgotten zone re-signing. Monitor everything. You should have alerts for signature expirations at least a week ahead, key age, DS mismatches, and validation failures. Use tools like Nagios, custom scripts, and external monitoring services. When DNSSEC fails, you need to know before your customers do. Document all your procedures obsessively, including the exact commands, registrar contacts, and escalation paths. At 3 a.m., you do not want to be figuring things out from memory. Test your procedures quarterly. Practice key rollovers, emergency procedures, and recovery scenarios. Think of them like fire drills. It is much better to find problems during practice, not during a real emergency. Choose your algorithms wisely. For example, ECDSA provides better performance than RSA set appropriate TTLs, like 1 hour for DNS keys and 24 hours for DS records. Always have rollback plans. Know exactly how to disable DNSSEC quickly, how to roll back keys, and how to change algorithms. It is also important to build relationships with your DNS chain, which includes your registrar support, DNS provider contacts, and operator communities. Start planning for post-quantum cryptography now. And finally, educate your team. Make sure that multiple people understand DNSSEC. Remember why DNSSEC matters. It prevents real attacks that cause real damage. Every single unsigned domain is a potential victim. Yes, it can be complex and frustrating, but it is necessary for a secure internet. We are the guardians of user security, and that responsibility demands implementing technologies like DNSSEC. DNSSEC is quickly becoming table stakes for any serious operation. Just as HTTPS became mandatory, DNSSEC will too. Organizations that implement it now are building crucial operational experience while the pressure is still low. Within 5 years, DNSSEC will be just as standard as HTTP pages. The only question is how many attacks we will have to endure before we reach universal deployment. DNSSEC is a journey, not a destination. Protocols will evolve, tools will improve, and best practices will be refined. Stay engaged with the community, keep learning, and share your experiences. Together, we are building a more secure internet, one signed zone at a time. Thank you for your attendance. Please consider subscribing to the channel.